Let's take another look at the equation ax equals b and what that implies about both the right-hand sides of that equation and about the solutions of that equation. But in so doing, we are going to uncover a fundamental concept, the linear independence of vectors. Let's start with right-hand sides of the equation ax equals b. The first thing we'll do is we'll rewrite our equation in column view. And in column view, what we see is B is a linear combination of the columns of A. Let's look at a quick example. Here's my system A, x equals an arbitrary right-hand side B. And when I rewrite that in column view, I see that that vector B is x1 times the first column of A plus x2 times the second column of A, all the way to x4 times the last column of A. And the important thing to notice now is if I plug in any possible x's into that expression, what that says is that B is in the span of these vectors. B is in the span of the columns of A. We'll allow the x's to take all possible values, and therefore let's write that as a theorem. If I start with my matrix of size m by n, with columns A1 through AN, then that system AX equals B. In order for it to have solutions, the B must be in the span of the columns. That raises a question. What can we say about the span of the columns of A? Well, for one thing, a span we know is a hyperplane through the origin. So B must belong to this hyperplane. And the second thing we know is that AX equals B is consistent whenever A has a pivot in every row. So that solution of AX equals B will exist for all possible B's if A has a pivot in every row. And that means that the span of the columns of A is the whole space. Well, how about the other case? If I don't have a pivot in every row, that is, if A reduces to row echelon form, but it has one or more zero rows. And the easiest way to get at that is to look at an example. Here is a system that I've set up with an arbitrary right-hand side, and we're going to do Gaussian elimination as usual. So my pivot, introduce zeros below the pivot, next pivot, introduce zeros below the pivot, and look what happened in this particular case. I find a row of zeros, and then my right-hand side is some combination of the entries in the B vector. As a consequence, in order for this system to have a solution, this right-hand side must equal 0. Let's say we do our computations in R, then I know that I cannot reach all possible right-hand sides. There are vectors B that do not satisfy minus 2b1 minus b2 plus b3 equal to 0. Is that always the case? Well, the easiest way is to realize that since my Gaussian elimination procedure here, each level is equivalent to the previous one, we know we can run this whole thing backwards. So let's start at the bottom. Let's start with a row of zeros and choose a vector on the right-hand side that is inconsistent. So I have to have a non-zero entry in the third row. So for example, I throw in the vector 1, 0, 1. I know I have a system that does not have a solution. The first step we had done is we'd subtracted out the second row from the third row. So let's add it back in. That gets us back to this level. And then what we had done is subtract out minus 2 times the first row from the second row and minus 4 times the first row from the third row. So let's add them back in, and we recover the original equation. And therefore, A times X equals this particular B vector will not have a solution. So if I start with an inconsistent system, if I start with a system that has a row of zeros, I can always do that. I can always go backwards and find some vector for which the system is inconsistent. If I don't have a pivot in every row, I will always have B vectors for which AX equals B does not have solutions. Let's see what we just did. We took AX equals B with a parameterized right-hand side, so arbitrary vector B. And when we ran our Gaussian elimination procedure, we found that that system will have a solution if and only if the right-hand side that we ended up with is equal to 0. And if I look at that equation here, I recognize it as a plane in 3 space. Usually you might think of it as minus 2x minus y plus z equals 0. My variables here are called b1, b2, b3. So not every right-hand side is in the span of the columns of A. And that span, in this case, is a plane in 3 space. We also found that if I have a row of zeros, I can always show that there are vectors for which Ax equals b is inconsistent. We get the following theorem out of this. Let's start with our matrix A of size m by n, and let's say it has a pivot in every row. If it has a pivot in every row, then Ax equals b is consistent for every right-hand side, and so is consistent for all the b's in my space in Fm. On the other hand, if I have one or more rows of zeros, then we know that Ax equals b is inconsistent for some right-hand sides in that space. There will always be vectors in Fm that we cannot reach by computing A times some x. Let's quickly review the number of solutions that we find as a function of the pivots in the matrix A. The first thing that we had found was that the system is consistent if any rows of zeros, if I have a row of zeros in my row echelon form, then the right-hand sides must equal to 0. As long as that's the case, I do have solutions for that system. Then, in terms of how many solutions I have for a consistent system, well, that depends on the presence or absence of free variables, meaning of pivots in every column. If I don't have any free variables, so I have a pivot in every column, then the solution is unique. If I do have free variables, there are columns without a pivot, then I have an infinite number of solutions. Let's look at a quick example. Here is a matrix augmented by B, and I have two parameters in that matrix, K and H. And I want to discuss the number of solutions I get for this system depending on the value of those parameters. So we'll just do Gaussian elimination as usual. So let's see. We set up our system, we find the first pivot at position 1, 1, and we eliminate underneath it, and so we come to our second level. And so my pivot now ought to be k minus 4. Well, if k is equal to 4, that's 0. That's not a pivot. So what I have to do at this point is either split this derivation into two parts, set k equals 4, and look at that case, and set k different from 4, in which case that would be a pivot, and look at that case separately. So I'd have to split it. However, if I allow myself to do partial pivoting, then I notice that I have a perfectly good pivot underneath. I have this 1. So let's interchange rows 2 and 3. And now I have a nice pivot 1 in the position 2, 2. And I'll use that to eliminate. So I simply say 4 minus k times the second row. And it doesn't matter whether that's 0 or not. Add it to the third row. I can always carry out this multiplication. And I get this system here. And now I am in row echelon form, and whether or not I have a row of zeros will now depend on 9k minus 36, so whether that value is 0 or not. When I now discuss what I have, is I see the following cases. First of all, let's look at that possible pivot in row number 3. It's either a row of zeros or not. If it's not a row of zeros, that means that 9k is different from 36, so k is different from 4. Now I have a pivot in every row, and I can solve no matter what the h is on the other side. Right? So I have a unique solution for every possible value of h. If 9k minus 36 is 0, so if k happens to be 4, then I have a row of zeros equal to some right-hand side. Plugging k equals 4, so h minus 2. Well, now it depends on the value of that right-hand side. If the right-hand side happens to be 0, my system is consistent, and I have a missing pivot and therefore an infinite number of solutions. Whereas if the right-hand side is non-zero, I have no solution. So overall then, if k is different from 0, I have a unique solution for every h value. If k happens to be 0, then it depends on h. If h is 2, I have a consistent system with an infinite number of solutions. If h is different from 2, then I have a non-zero right-hand side. I have an equation 0 equal to a non-zero right-hand side, and I have no solution. Next, let's look at the solutions again. We know that when we do Gaussian elimination, we always find a solution that looks like this. x is equal to a constant vector plus for each one of my free variables, alpha 1 times a vector, alpha 2 times a vector, etc., for however many free variables I have, let's say k. The alphas, of course, are arbitrary parameters. To further analyze this solution, I need a theorem, namely that if I take a and a vector x and a vector y, if I want to compute a applied to the sum of those two vectors, I can compute them individually as a applied to the first vector plus a applied to the second. Similarly, a applied to alpha x equals alpha times a applied to x. If we now apply this theorem to our solution, we see the following. A applied to x, therefore, is a solution. If I set all the free variables equal to 0, then xp is also a solution. So a times xp must equal to b. And now let's look at what happens when I look at the difference. A applied to x minus that vector xp. By my theorem above, that's just ax minus axp. And ax, since x is a solution, that's b. xp is a solution, that's also b. And so a applied to x minus xp is equal to 0. But x minus xp, that's the expression multiplied by the alphas. So that expression multiplied by the alphas is the solution of ax equals 0. We give that solution a name. We call this the homogeneous solution to the homogeneous problem, ax equals 0. We have this definition. Any one solution, in particular xp, is called a particular solution of A. Of course, xp is not unique. If I set, say, all the alphas equal to 1, I will have a solution. I will have a particular solution for that system. The part of the solution that's multiplied by the alphas, that corresponds to the free variables, is the homogeneous solution for the homogeneous system ax equals 0. And what I want you to notice is that if I plug x equals 0 into that equation ax equals 0, x equals 0 is always a solution. It's called a trivial solution. It corresponds to setting all the free variables equal to 0. Let's look at a quick example. We had found a solution to a system in section 2.2 of the previous lecture. We had 5 variables. 2 of them are free, namely x3 and x5, and the solution we found took the form a constant vector, our particular solution, plus alpha times a vector, beta times a vector, our homogeneous solution, all the possible homogeneous solutions. So the particular solution I get by setting the free variables equal to 0, by setting alpha equal to 0 and beta equal to 0. But what are the free variables? They are x3 and x5. So the particular solution I get by setting the free variables equal to 0. The particular solution, the way we construct it, has zeros for each of the free variables. Now let's look at the homogeneous solution. It solves ax equals 0. If I take alpha equals 1, the first free variable equal to 1, and beta equal to 0, I'll get that first vector as the solution of the system ax equals 0. And therefore, I have the first free variable equal to 1 and the second free variable equal to 0 in my first solution. Similarly, for the second one, the second vector I get by setting alpha equal to 0, therefore x3 equals 0, and beta equal to 1, that is, x5 equal to 1. And so what I see in my solution here is that I have a pattern of the entries. In the particular solution, the free variables are equal to 0. Then in the homogeneous solution, the first vector will have 1 for that first free variable and zeros for the others. And the next vector will have 1 for its free variable and 0 for the others. And for more vectors, that pattern will continue. What I see is I have columns of I sitting in my homogeneous solution vectors. And that is going to work no matter how many free variables I have. With k free variables, we just get more and more columns of I. So where we are now is that for every right-hand side B in the span of the columns of A, so as long as I have a solution, then the set of solutions, x equals xp plus xh, that's a hyperplane. If you look, xh is a span of 2 vectors here. It's a hyperplane in R5. And that plane is pushed away from the origin by a constant vector. So where we end up, therefore, is a consistent system. The B's must live in a hyperplane in Fm, and the solutions for any one B in that hyperplane will take the form of a hyperplane pushed away from the origin by a particular solution. When there are no free variables, that is, when A has a pivot in every column, then the homogeneous solution is just a trivial solution. Let's next look at non-trivial homogeneous solution. To understand the homogeneous solutions a little bit better, let's look at Ax equals 0 in column view. So take A, split out the columns A1, A2 through AK, and rewrite our equation as a linear combination of the A's equal to the 0 vector. And here I put in the parentheses just to emphasize that these A's are vectors. Then if there's a non-zero solution, so if there are some x's that are non-zero that satisfies that equation, let's say the first one is non-zero, then I can solve for A1 in terms of the other vectors. So I can say that the first column A is equal to a linear combination of the remaining columns. To make it clearer, here's an example. So I start with Ax equals 0. I represent it in column view. Here it is. And I solve the system. Among others, I see a solution -1, -1, 0, 1. If I plug that solution in here, what I see is -1 times the first vector, -1 times the second vector, plus 0 times the third, plus 1 times the fourth, indeed add up to 0. And as a consequence, I can pick one of those vectors that doesn't have a 0 multiplier and solve for it. So for example, if I take 2, 1, 5, the second vector, I can solve for it in terms of the other vectors. That vector 2, 1, 5 is a linear combination of the other vectors. So what we see then is that the homogeneous problem has a non-zero solution if and only if there's a column in my matrix A that can be rewritten as a linear combination of the other columns. And that is a big result, so big in fact that will make this a definition. So we'll start not with matrices but with vectors. Given a set of vectors v1 through vk, we are going to form the equation linear combination of those vectors with arbitrary coefficients alpha 1, alpha 2, alpha k, and set that equal to 0. Okay, so I have an equation for the alphas here. And I'm going to look at solutions for that equation. One solution, of course, is that all the alphas are equal to 0. The other case is if I find non-zero solutions. If there are some alphas that are different from 0, so that this expression indeed adds up to 0. If that's the case, then I'm going to say that the vectors are linearly dependent. On the other hand, if the only solution is all the alphas equal to 0, we will say that the vectors are linearly independent. So looking at my previous example, I see that there is a linear combination of the vectors that adds up to 0 with whatever the coefficients are. One of them happens to be 0. And since that's the case, these vectors are linearly dependent. And when the vectors are linearly dependent, it means that there is a vector with a non-zero coefficient that I therefore can solve for. I can take that vector and express it as a linear combination of the other vectors. What we'll do now is we'll recover our original motivation for the definition, namely we'll take our vectors and we'll write them into a matrix as columns. So A is equal to first column V1, second column V2, etc. The variables, alpha 1, alpha 2 through alpha k, we'll write into a vector, and we'll call that x. And therefore, we are going to recover A times x equals 0. So we have rewritten our linear combination of vectors in matrix form as A times x, and we are asking that that add up to 0. And so the definition above says that the columns of A are linearly independent if and only if Ax equals 0 has only the trivial solution x equals 0. That is, the unique solution x equals 0. The moment I have a non-zero solution for Ax equals 0, the vectors are dependent. A theorem, therefore, a set of vectors in Fm is linearly independent if the solution that I get by writing these vectors into a matrix as columns, if that has only the trivial solution x equals 0, and what that means is that that matrix has a pivot in every column. My problem, therefore, my question, are vectors linearly independent, yes or no, has been reduced to asking, does the matrix that I form from those vectors, does it have pivots in every column? If yes, the vectors are independent. If no, the vectors are dependent. So let's look at a few examples. First, Ax equals b in general. So let's look at just solving a problem like that. So here's a set of vectors, and we're asking, are they linearly dependent? And I wrote them as rows on purpose to just emphasize that I have to assemble my matrix A by writing these vectors into that matrix as columns. So here it is. And now we run Gaussian elimination because we're after the pivots. So we introduce zeros in the first column, introduce the zeros in the second and the third. And at the end of it, when I'm in row echelon form, I see a pivot in every column. And so the answer here is yes, these vectors are linearly independent. If I try and write Ax equals 0, if I try and write a linear combination of these vectors and set it equal to 0, the only way I get 0 is by multiplying each one of the vectors by 0. A case where the vectors are linearly dependent, well, here, a slightly different set of vectors, and again, I'll write them into my matrix as columns. I'll run Gaussian elimination, and at the end of Gaussian elimination, I see that there are columns here that do not have pivots in them. So the first column has a pivot, the third column has a pivot, and since there are columns without a pivot, the vectors are linearly dependent. One thing I want to point out here is that if I get rid of two of the vectors here, let's say I get rid of the second vector and the fourth vector, that eliminates the second column and the fourth column in here, but it leaves the elimination steps intact. So the first vector and the third vector, that set, is linearly independent. They have pivots in them. Or the first vector and the fourth vector, if I get rid of the two vectors in between, I see a pivot in every column. So the first vector and the fourth vector, that set would be linearly independent. So I can pull out subsets of those vectors that are linearly independent. Next, let's look at some special cases, because there are cases where we can answer immediately without doing any special work. So my first example is, let's suppose I give myself a set of vectors, and it has the zero vector as part of the vectors. The moment I have the zero vector, if I want to write a linear combination of these vectors and set it equal to 0, that zero vector can have any multiplier I care to put in. So 0 times the first vector plus 0 times the second vector plus 1 times the zero vector certainly adds up to 0 and is a non-zero solution of the arbitrary linear combination of these vectors equal to 0. So the moment I have the zero vector in the set is linearly dependent. Next, let us look at the following case. I've got my vectors v1, v2, v3, and I showed a subset of the entries in those vectors in red, because when I assemble these vectors in a matrix, look what I have. The red submatrix here is triangular, 2, 0, 0, 5, 3, 0, 3, 8, 3. So I have a triangular submatrix in my matrix A. And when I set up my linear combination of vectors and force it equal to 0, then that submatrix, if I just look at the submatrix itself, I see the equations 2 times alpha 1 equals 0, 5 alpha 1 plus 3 alpha 2 equals 0, and my third equation here. And when I try and solve, well, the first equation says alpha 1 equals 0, so now alpha 1 is gone. That forces alpha 2 equals 0, so now alpha 1 and alpha 2 are equal to 0. That forces alpha 3 equals 0, and therefore I have unique solution, all the alphas equal to 0. So the moment I have a triangular submatrix in my vectors, I know the vectors are linearly independent. Super special case, the submatrix is not just triangular, the submatrix is diagonal, my vectors are linearly independent. The next case is if I happen to recognize a relationship between the vectors. So if I look at my vectors v1, v2, and v3, I might notice that the first vector plus 2 times the second vector adds up to the third one. 1 plus 10 is 11, 2 plus 4 is 6, 3 plus 6 is 9, 4 plus 4 is 8. So I have a linear relationship between the vectors. I can write v3 as a linear combination of v1 plus 2v2. And pulling everything to the same side, I see that v1 plus 2v2 minus v3 plus 0v4 is equal to 0. I have a non-zero solution to my linear combination of vectors set equal to 0. Or, even more extreme, if I notice that, hey, wait a second, the first vector is equal to the fourth vector. v1 is equal to v4. If I try to push everything to the other side and write the linear combination, I see v1 plus 0v2 plus 0v3 minus v4 is equal to 0. Again, my definition for linearly independence, I have a non-zero solution for arbitrary linear combination equal to 0. The vectors are obviously linearly dependent. The next example goes like this. Suppose I have 4 vectors here, and the vectors are in R3. Right? When I put them into a matrix, how many pivots can I have? Well, at most 1 pivot in every row. Therefore, at most 3 pivots. I have 4 vectors. Only 3 pivots, or at most 3 pivots. There's going to be at least one of these columns that doesn't have a pivot in it. Since it doesn't have a pivot in it, I have a set of vectors that must be linearly dependent. And that, of course, works no matter what the sizes are. As long as I have more vectors than entries in the vectors, my set of vectors is linearly dependent. So let's write this as a theorem. I'll give myself n vectors with m entries each. If I have more vectors than entries in a vector, then my vectors are linearly dependent. The last example had to do with the pattern of ones and zeros that I see in the homogeneous solution that I construct by back substitution. We saw above that when we construct a solution by back substitution, that the homogeneous vectors have I inside of them. Have a diagonal matrix with all ones inside of them. The homogeneous solution vectors that we obtain by back substitution are linearly independent by construction. They contain successive columns of I. The takeaway then? Well, we found a number of hyperplanes associated with AX equals B. That the first remark was that AX equals B is consistent only if B is in the span of the columns of A. So it's only if B is in a hyperplane through the origin. Of course, if A has a pivot in every row, that means that that hyperplane is all of Fn, is the whole space. However, if A doesn't have a pivot in every row, then that hyperplane is a proper hyperplane in the space. There will be points in the space that we cannot reach by computing A times some x. There will be no solution for those vectors AX equals B. The other hyperplane we found was for the x's rather than the b's. That the solution of AX equals B always has the form x equals xp plus xh, where xp is a particular solution and xh is all the homogeneous solutions. And that means that the homogeneous solutions, they are a hyperplane through the origin, and the solutions for some particular b that we get there for is this hyperplane through the origin, the homogeneous solution, pushed away from the origin by that vector xp. The second thing we found, and that's the most important part of this lecture, is that there's a relationship between vectors that plays a central role in what we'll do from here on out. The concept of linearly independent vectors. And so just to remind you what the definition meant, a set of vectors is linearly dependent if and only if there's at least one of those vectors in that list that I can write as a linear combination of the other vectors. The moment that's the case, my vectors are linearly dependent. If I can't do that, all the vectors are linearly independent.